this is chapter 5.3.3, where we are going to use partial fraction expansion to find the inverse Z transform. Typically, we're given a Z representation as a rational function of a numerator power of Z with over the denominator power of Z, where Z can be in positive Z power or negative Z power. It doesn't really matter. We can convert one to the other. Now we need to know and remind ourselves what are the important terms, which is zeros and poles of x of z. So the zeros of x of z is simply the roots, that means the values of z that will make the numerator equals to 0. So let's have an example. So we have z minus 1 over z minus or z plus half. The values, the roots of numerator is, in this example, z is equals to 1. Because when we substitute z is equals to 1 here, then the numerator becomes 0 and the whole expression becomes 0. So z equals to 1 is the root of the numerator. What about the bottom? Well, when in this example, when z equals to minus half, then the denominator becomes 0. So when z equals to minus half, the denominator becomes 0. So on top is z is also half, minus 1 is minus 1 half divided by 0 is infinity. So z equals to minus half is the root of the denominator, but also causes x of z to become infinity. Hence we call it the pole of x of z. So typically we want you to sketch the pole and 0, and when you want to sketch the pole and 0, it is better to represent this as positive power of z. So if you have negative power of z, then you try to convert it into positive power of z. Alright, additionally, when we want to use partial fraction expansion, then x of z must be as a proper rational. That means the power of z on the numerator must be less than, here the word is smaller, than the degree of the power of the denominator polynomial. So if this is not so, then what we can do is that we'll perform long division until it is satisfied. Alright, so the first idea is that we're given x of z as two polynomial. In this example, we are using negative power of z in the polynomial, and we have degree m and degree n. And we have a proper rational function when m, the numerator, is less than n. If it is not, we must perform long division here, and then we will basically get in here the polynomial that is proper form. The numerator is less than the denominator. At least we're talking about the power here, and we have another expression here. Okay, so we are decomposing this rational function into two parts, such that this part would have a power that is less than the denominator. Alright, let's see an example. The first example is this guy. We are having negative powers of z here, and this is xz. So this is nz, numerator, and this is denominator. The degree is 2, here is 1. So the degree is higher than the bottom one. We have to convert it into two parts. One part is also rational function, which is the numerator power is in here is 0, therefore 0 is less than minus 1. Is less than 1. So what happened is that this is a proper rational function. Now, how do you do that? Well, one way to check is this. You take this expression and you'll get this expression when you collapse the denominator together. Okay, so to check, simply do this. It is minus 1 multiplied by 1 plus 2z minus 1. So this is actually 4. 1 plus 2z minus 1 then this guy is, you will do 2z minus 1. So bottom is 4. 1 plus 2z minus 1. 1 plus 2z minus 1. And the last expression is, so you want to also have a common denominator. So it is 4 times 5 over 4. And the bottom is 4. 1 plus 2z minus 1. Now if you work this out and you simplify, you will get this expression over here on the left. Now how to go from here to this expression is simply by long division. Okay, you can try it out by yourself. Now, I'm going to use MATLAB to solve my problem. Of course, using MATLAB is only possible when you're in the lab or you're just verifying your answers. So let's see how we're going to use MATLAB. So we have a numerator here, and we are going to call this numerator, and we are going to use the coefficients of this 1 and 1 here, but at different positions of the vector. So the first one is this red one here. So this one is this one with index power 0. So this is at the first position. There is no index power at z minus 1, so we will put 0 here. What about the last guy? I'm going to use green now. So green is 1, z minus 2. So the last guy is here. So this is index for power 0. This is index for power equals to 1. This is index for power equals to 2. I should say minus 2. So this green guy represents this. This red guy represents this for the numerator. Okay, so I have numerator 101. What the denominator? It is. Now let's try the denominator now. I'm going to use the denominator, and it will be denominator is equals to 1, 0, 2. The first one is for this one. There's no, I made a mistake, sorry. It should be 1 and 2, because 2 is for this 2 at index 1. So we have numerator 101, denominator 12. So what do I do with it? Well, see, this is what I did. 101 for the numerator, denominator 12, and I'm going to substitute into this MATLAB function called residual z to perform the partial fraction expansion for me. This is different in Laplace transform. In Laplace transform, I use residual. There's no z there. Here, why am I using residual z? In residual z, I must have the expression in negative powers of z. So it must be in this form. While in the Laplace, it was in positive powers of s. So there are slight difference here. Okay, so if you want to express this as negative power of z, then we use residual z. Alright, let's see what residual z do. So let's me put here again, and this guy is 1, 2. Out comes RPK, very similar to our residual. Okay, so let's read. In the residual of z, this is what it says. First, I express it as some b over a, where b over a's are vectors representing the terms in the polynomial. And this polynomial must be in the power of ascending power of z minus 1. Okay. Now, once I put b and a, out comes RPK. What is R? R is here, is a vector, and the first element of the vector is here, divided by 1 minus the first element of the pole P is here. So R is on top, P is below. Correspondingly, R1 over P1, 1 minus P1, Z minus 1. So R2, R3 will be with respect to Rn over Pn. Now, what about K? So K will be also a vector, and out comes K1 here. K2 will be Z minus 1. K3 will be Z to the power of minus 3, and so on. So that's the idea. Alright, let's have an example. We substitute this expression in, and out comes R is one of them only, 1.25. P is minus 2. So I'm going to do 1.25 divided by 1 minus, what is P? Minus 2. Minus 2, Z minus 1. So this is my first expression here. Plus, what about K? K has two expressions. So plus, it will be minus 0.25. The first K has nothing. No, it's not some Z. So the second K has plus half Z minus 1. So this is the answer of x of Z equals to 1 plus Z minus 2 over 1 plus 2Z minus 2. So it converts a rational function and into partial fraction expansion into all these forms. And in all these forms, I can then perform inverse Z transform. So in this course, I mean, you need to do partial fractions by yourself from here to here. But what I'm showing you is that you can use MATLAB to do this by yourself and for checking. And you'll realize that once I have it in this form, then I can convert by the inverse Z transform lookup table to get each of these expressions. Thank you.